think we'll give people just another minute or two to filter back in before we start.
Can I share my screen meanwhile?
Yeah, of course. I think we can go ahead and get started. Our last talk is going to be by David Mwakima on Berkeley and infinite divisibility. And he wanted to give a short presentation live, so I'll pass it over to you, David.
Okay, thank you, Aaron. So my plan is to just give an overview of what I'm up to in this paper for 25 minutes. And then the rest of the 30 minutes that I've been given for my talk, we can ask questions, and I'll try to see whether I have an answer. So let's go. So Berkeley on infinite divisibility. The story begins with Aristotle. So Aristotle, famously in the physics, takes infinite divisibility and continuity to be synonymous. So I have some quotations here. What is infinite divisible is continuous. What is continuous is divisible ad infinitum. By continuous, I mean that which is divisible into divisible is always divisible. We take this as a definition of continuous. So what happened is that this Aristotelian view of infinite divisibility of continuous quantities was adopted by Isaac Barrow, who was a professor at Cambridge in the 17th century. He maintained and argued at length that whatever is continued is always divisible into parts, again, divisible. And he says that he's not ignorant how difficult this doctrine is admitted by some and rejected by others. So Berkeley was one of the people who rejected this view. He begins his account of mathematics actually in the principles of human, concerning the principles of human knowledge by saying that infinite divisibility is neither an axiom or theorem of the elements of that science. And I took this to mean that if we go back and look at Euclid's elements, then we shall not find any evidence of infinite divisibility as a theorem or axiom. And this is, in fact, applying the face of people like Arnold and Nicole, who in their logical art of thinking maintain that geometry provides proofs as clear as proofs of any other tool. It reveals to us that infinite divisibility, here they're talking about matter, has been demonstrated. So the question I'm asking in my paper is whether infinite divisibility of finite lines is an axiom or theorem of elementary geometry. I argue that Berkeley is right in pointing out that it is neither an axiom nor theorem. The view that magnitudes are infinitely divisible is a philosophical thesis due to Aristotle. The reason why I emphasize philosophical thesis is because Aristotle was, he was developing this view in response to the atomists. So the atomists, who are Aristotle's most, the people that he was objecting to the most, held that they are indivisible atoms that compose continuous quantities of matter. And Aristotle was actually developing a view that was supposed to deny that quantities or magnitudes of matter is atomic. So why does this matter? Well, I think it matters because Berkeley is telling us that there are certain prejudices that have passed into principles. And one of those is the infinite divisibility of quantities. And Berkeley is asking us to actually question this principle to find out whether indeed it is true. The other reason why it matters is I think that if you look at the literature on this subject, many of the authors that have written on Berkeley actually take this denial of indivisibility as one part of Berkeley's thinking, where he was a bit too radical in his foundations for geometry. But I don't think that they have evaluated in detail whether this is in fact an axiom or theorem in Euclid. Many of them have assumed that it is. Again, I also think that it is hard to understand Berkeley's mathematical atomism without understanding the history of mathematics, especially the view of the Pythagoreans and how that relates to Aristotle, and especially the influence of Gassendi. I think Gassendi was one of the people in the 17th century who was trying to distinguish between the thesis on the mathematical side regarding infinite divisibility and the thesis of infinite divisibility on the physics side. And I think Berkeley was aware that there is such a distinction and we need to maintain it. So how have I outlined my presentation? So in the first part, I introduced the terms which set this debate. And I will want to argue that it depends on how we conceive of points and how we understand the relation of part to whole. So in the second part, I show briefly, because I don't think I'll have time to go into any detail, how Aristotle's conception of mathematics led him to the thesis of infinite divisibility. And the conception here is a philosophical conception, because it is defended at length, first in the categories and subsequently in the metaphysics and the physics. And then I will conclude briefly by looking at the debate between Berkeley and Barrow on incommensurables. If you recall the quotation we saw from the portrayal logicians, it was incommensurability that implied infinite divisibility. So I would want to see whether that is in fact the case by looking at this debate between Berkeley and Barrow. So let's start. So in the principles, we get a very compressed argument by Berkeley regarding infinite divisibility. So it's compressed because I think Berkeley had exercised his thinking on this subject very early on in his career, starting in the notebooks through and so on and so forth. That's why in the notebooks in particular, so you find him really exercising himself on this question. So when you get to the principles, we get the first argument that this is the first argument. What I'm calling the first argument is the one that comes from principles 128. So there are no infinite lines. That's the premise. So suppose that a line L is infinitely divisible into an infinite number of parts. Then the union of that infinite number of parts is finite. So it follows that the line L is infinite. So the premise one is contradicted because it's common ground, presumably, that there are no infinite lines. But then the second argument, which is suppose or let L be a finite line, and suppose that L is infinitely divisible into an infinite number of parts. Again, the union with the number of parts is finite. It follows that line L is infinite, contradicting the first premise. So one has several ways of rejecting these arguments. One can deny that it is common ground in the 17th century, that there are no infinite lines. And so Anat Shetman has argued in a recent paper on 3 types of infinity in the early modern period, that Locke accepts the notion of an infinite measure. So I think in that paper, she wants to argue that Locke accepts this notion of infinite measure. Leibniz denies it, but has instead an iterative notion of the infinite. And, but he denies the notion of an infinite measure. And then Descartes has a notion of an ontic measure. So I think, so if you read Shetman's paper, you might think, oh, well, look, perhaps it was not common ground in the 17th century that there are no infinite lines. And there's evidence, if you look at the essay, Locke does write that space in itself is actually boundless. But crucially, I think the argument that there are no infinite lines depends on the assumption of whether space is a magnitude. And I think there's evidence that it is, because space is continuous. But if it is a magnitude, then the infinitude of space is ruled out by Eudoxus' axiom. Because this axiom, which we find in Euclid book 5, definition 4, says that ratios are only defined between finite magnitudes. And this is captured by Mancosu in a slogan, which he thinks goes back to the 17th century, that there is no proportion between the finite and the infinite. So if this was the case, then I think it is common ground that there are no infinite lines, regardless of what Locke had to say about infinite measure and so on and so forth. But another reason people argue that Berkeley is mistaken challenges the premise that the union of infinite parts, of an infinite number of parts is infinite. So people point out that Berkeley betrays a naive ignorance of convergent geometric series. So convergent geometric series have a finite sum, even though there is an infinite number of parts in a line, for example, that has been divided in the ratio 1:2. So how I respond to this criticism that Berkeley betrays this naive ignorance is that Berkeley, the elements, does not discuss the notions of convergence and divergence of infinite series. This came much, much later. It is Aristotle who was one of the first to use this convergent geometric series as synonymous with potentially infinite divisible as a response to Zeno. So again, here we are seeing a kind of philosophical argument being made on the basis of mathematics. So there's kind of conflation going on. But I also think that Berkeley read Barrow's mathematical lectures. So the fact that he read Barrow's mathematical lectures, I think, counts as evidence that he was not simply ignorant that convergent geometric series might be counterexamples. So there must be something else that's going on. And what I think is going on is that this whole issue turns out on the question of points and whether points can actually compose a magnitude. So in order for me to do that, I need to be clear on what Berkeley's denial of infinite divisibility entails. So many have supposed that Berkeley's denial entails that for every line, there is a finite number of divisions that can be done on L, beyond which L is not divisible. But I think this can't be right because Berkeley doesn't think they are indivisible lines. So his geometrical minima are points, they're not lines. So what I think Berkeley's denial of infinite divisibility entails is that lines can be composed of indivisible points or geometrical minima. The division of a line can't go on infinitely because eventually, contrary Aristotle, we must arrive at mathematical atoms or points. So I'm good to show in what follows that Aristotle's thesis regarding infinite divisibility denies that continuous quantities are fundamentally atomic. Specifically, it is equivalent to the thesis that lines cannot be composed of points. So the evidence I have is the following. So in the book that deals with continuity, Aristotle is explicit. He's explicitly saying that nothing that is continuous can be composed of indivisibles. A line cannot be composed of points, the line being continuous and the point indivisible. And so the argument that he gives at this section of the physics depend on subtle distinctions that Aristotle had made leading up to this book, namely the difference between being in contact and the difference between holes and the difference between succession and so on and so forth. But the whole point is that he wants to argue that the infinite divisibility of continuous quantities rules out that points can be composed of points. So instead, Aristotle proposes or argues that points exist potentially. I already mentioned this earlier when I was beginning my talk. And the evidence I have for this potential existence of points comes from commentators on Aristotle's physics. In particular, Simplicius was in the 6th century Common Era, has this to say in his commentary on Aristotle's physics. But even more recently, scholars of Aristotle, like Fred Miller Jr., noticed that Aristotle is reformulating all these difficulties in his own terms. and presents his own theory of the continuum as the only way out of this ancient dilemma, which seeks to show the absurdity of continuous magnitudes. So the ancient dilemma is the following. If someone says that mathematical points can have no size or spatial extension, then they are nothing and cannot be parts of magnitudes. For the parts of magnitudes are other homogeneous magnitudes with size. But the second one is that if someone says that mathematical points have size, then they are not indivisible after all. So Aristotle rejected the first horn and reanalyzed continuity in terms of infinite divisibility and avoided the dilemma by arguing that points exist potentially. Epicureans and Berkeley embraced the second horn, but avoided the dilemma by saying that points have the minimal size beyond which magnitudes cannot be divided. That is, they denied infinite divisibility. So Aristotle defended his view of potential existence of points on the basis of the bisection theorem. So Aristotle assumed that you can always bisect a line into two equal segments, and the continuity consisted of the identity of the right limit of the left segment and the left limit of the right segment. But Aristotle additionally drew the conclusion that continuous magnitudes are infinitely divisible on the basis of the claim that bisections can be done an indefinite number of times. And geometers following Aristotle took this to be the consequence of what is now the proposition in the Euclid's elements that involves bisecting a given line. So what I argue against this way of taking proposition 10 in Euclid's element as a proof of infinite divisibility is that the analysis of the proof does not show that a line can be bisected infinitely many times. I think we need to distinguish what we are in fact bisecting. In reality, for the bisection stage n greater than 1, we are strictly speaking not bisecting the original line. So it is false to say that bisections of the original line can be done infinitely many times. For each line, the bisection is only done once. But it is possible that Aristotle was using a different geometry textbook by Theudius, where the conclusion was, in fact, that this process can be done infinitely many times. So recent scholars like Linebo and Shapiro speculate that in holding that these procedures can be iterated indefinitely, Aristotle again follows the mathematical practice of the time, this time in opposition to his major opponents, the atomists, who postulate a limit to, say, bisection. But as a way of responding to this reading of Linebo and Shapiro, I think Proclus, whose commentary on the first book of Euclid's Elements is the best historical source we have of ancient geometry, has this to say. So I'm not going to read the entire thing because of time, but I want us to focus on the sentence beginning with the continuous. So he says the continuous, we say, is what consists of parts that are in contact, and this can always be divided. But they do not assume that what is continuous is also divisible to infinity. It's an axiom that every continuum is divisible. Hence, a finite line being continuous is divisible. This is the notion that the author of the Elements uses in bisecting the finite straight line, not the assumption that it is divisible to infinity. That something is divisible and that it is divisible to infinity are not the same. And I think Proclus is right for the reasons that I gave earlier. Like, we need to distinguish between what we in fact bisecting or dividing. Though it is true that every line is divisible, but it is not necessarily true that every line or the same line is infinitely divisible. So in particular, what we get from Proclus is that continuity was a common notion required to argue that every line is divisible or bisectable once. Aristotle was one of those people who fallaciously made the extrapolation from the divisibility of each line to the potential infinite divisibility of the same line. And he analyzed continuity in his own terms because he held a different conceptions of mathematics from the Pythagoreans. Now, I will not go into these different conceptions of mathematics from the Pythagoreans. People who are interested can look at my paper. What I will want to finish up with is this debate between Berkeley and Barrow on incommensurables and infinite divisibility. The reason why this debate is important, because if Berkeley denies infinite divisibility, then according to most scholars, incommensurability poses a threat to him. And in particular, it's a threat for Berkeley if, one, he believes that they are indivisible lines, and two, he believes that the number of indivisible lines that a line can be divided into corresponds to its size. So for example, you can think of the diagonal of a square of unit length. If Berkeley believes both 1 and 2, then we can find the number of indivisible lines in the diagonal as, say, m, corresponding to its size. And then you can find the number of indivisible lines on the side corresponding to its size as n. But then it means that we can find a proportion or ratio between the diagonal and the side, which is impossible, especially if the square root of 2 is incommensurable with the unit or 1. So I think Berkeley can avoid this problem or this threat. One, because he doesn't believe they are indivisible lines. As I've mentioned, his geometrical minima are points. And although Berkeley appears to endorse 2, it is not because he believes in indivisible lines. Rather, he is thinking in metrical terms. Thinking in metrical terms is what I think Berkeley can make sense of Berkeley's reasoning when he says that the interval, or when it seems to imply that the interval between 0 and 5 is larger than the interval between 0 to 2. Although we know today that the same number of divisions can be made in each. Okay, I think I can go through this in more details during Q&A, but let me just finish for now. So on this debate. So Barrow, in his mathematical lectures, says that I shall briefly observe to you that all the arguments which are brought against the perceptual divisibility of quantity are either mere begging the question or depend upon false supposition, or lastly, have no relation at all to the matter. But Berkeley, in his notebooks, where, as I mentioned, he was really thinking about this issue very early on in his career, promises or tells himself that he needs to inquire most diligently concerning the incommensurability of diagonal and side, whether it does not go on the supposition of unit being divisible ad infinitum. That is, of the extended thing spoken of being divisible ad infinitum. And so the indivisibility of deduced therefrom is a petitio principii. So you might think that this is another instance where Berkeley is engaging in an ad hominem argument, but I think there's no fallacy here. We need to see who is right. I think we can do that. So because of what Barrow says in his mathematical lectures, he says that the principal reason of incommensurability seems to be founded in this, that since a mean proportional number may always be found between two plane similar numbers, because the product made by the multiplication of plane similar numbers is always a square number whose root is that mean proportional. Since I say things are thus in similar numbers and is demonstrated in the elements, that it happens quite always in all dissimilar numbers, there's no mean proportional number between two dissimilar plane numbers. Hence, if quantities are supposed to be to one another in the ratio of two dissimilar numbers, and a mean proportion will be found between these quantities, which may perpetually be done because, notice, because of the indivisibility of every quantity, there will be no number in universal nature which can represent or answer to this quantity. And consequently, those being supposed and expressed by numbers, this will be incommensurable. So Barrow's point is, I think, not as complicated as it sounds. It's really the question of finding the geometric mean between two numbers, which is I've shown on the third bullet point. So Barrow's point is that the geometric mean is rational just in case m and n are plane similar numbers. But if, again, if you look at the proof, this is book 8, proposition 11, nowhere in this proof is infinite divisibility of finite lines assumed or concluded. Again, we can get into this in Q&A. So recap and conclusion. What I have done is, again, in this project, is to look at the history of geometry to attempt to substantiate Berkeley's claims. I think I have shown that historically the debate turns on how we understand parts and points. And I showed that Aristotle's conceptualized mathematical concepts to suit his physical purposes, and that the view differed from the Pythagorean in this regard. And even divisibility was a consequence of this new conceptual framework. And the debate between Barrow and Berkeley is decided in Berkeley's favor. Thank you.
Great, thank you. For those that are just joining us now, we're adopting the convention of clicking on the raise hand icon if you have a question. And you can find that if you click on the participants thing, and then there's going to be a list, and then underneath that list will be the raise hand. But if you're having problems with that, or if you have a follow-up during any of the Q&A, feel free to just type it into the chat box and we'll get to you whenever we can. So if anybody has any question, go ahead and click on the raise hand thing and we'll go through the list. Kenny, you want to go ahead?
Sure. Thanks, David. I just have a question about the definition of bisection.
Yes.
Because if every line can be bisected,
Mm-hmm.
and to bisect a line means to construct two lines of equal length that are half the size of the original line, or to divide it, right, into two lines of equal length, then it will follow from that the lines are divisible to infinity, right? If the product of bisect line.
Okay, why though?
Well, because we divide it once, right? And when we divide it, what we've created are two lines that are each half of the original line.
That's true.
But
Mm-hmm.
since those two things are lines, they're also divisible in half. The operation of bisection can also be performed on them. And the output of the operation of bisection is a line, half the length of the original one. Right, so since the output again is a line, it's divisible again.
Okay, right. I think there's I do not disagree with that. I think what I'm saying in my paper is that this follows from a common notion, namely that every line is can be bisected or divisible. So it is true that we can generate an infinite number of lines through this process, all right? But it is one thing to say that we can generate an infinite number of lines through this process, right? And to say that the original line is infinitely divisible, because you're not dividing the, like, let me put it this way. Actually, let me pull up my slides. I think I have something to say on this in the later slide, which I did not show. Just give me a moment. Let's see. No, it's not there. Here, yeah, slide 27. So the bisection, we are strictly not bisecting the original line. So I'm taking that the theorem that we find in proposition 10, he says that for each line, right, we can bisect it, right? And that is true for each line, but it does not follow from that this can be done infinitely many times. We need a different argument that this can be done infinitely many times.
So that's the part I'm confused about.
Yes.
Because if the bisection divides the line in half,
mm-hmm.
and each of the halves are themselves lines, and every line can be bisected,
mm-hmm.
then we get infinite divisibility, right? So which step of that goes wrong?
Wait, so infinite divisibility in which sense? In the Aristotelian sense or from proposition 10? So in the Aristotelian sense of infinite divisibility, what we're getting is that we cannot have a line composed of points. And I'm saying that that does not follow from proposition 10.
I'm not sure I understand the distinction between the senses of infinite divisibility.
I think Scott has a follow-up on this that might help.
Yeah, maybe that'll help.
Okay, yeah.
Yeah, so I had a similar sort of question. I had it in slightly different terms. So the bisection of the line, you take a line and you bisect it. The two bisections of it are, could we call them parts of the original line?
The resulting two lines, yes, are parts.
Okay, so I feel like there's a similar thing we can say about this to Kenny's question, which is if it's a part of the line, then bisecting it is also a division of the original line, right? So if you bisect the bisection of the original line, isn't that, it's not a bisection of the original line, but it is a division of the original line. And it seems like you can continue to bisect the parts infinitely. And so it should be, you should get the result of infinite divisibility.
Okay, so, all right, okay. I'm seeing what you're saying. So suppose you have a line AB, you bisect it at C. Now we have, how many lines? We have 3 lines, AC, CB, and the original line AB. Okay, so what are we bisecting next? Are we bisecting AB, or are we bisecting AC, or are we bisecting CB?
Bisect AC at point D, then bisect AD at point E, then bisect AE, right? And you can keep doing that forever.
That's right, but notice it's not the same line that we are dividing. Here we are dividing any of the two resulting lines from the preceding bisection. And I think this is the distinction we are getting here. And I agree with Kenny and Scott's questions that this is a tricky way of understanding what's going on. But the reason why I think we need to dissociate the two is because for Aristotle, when he's trying to argue against the atomists in the physics book 6, what we have is that he thinks the dichotomy paradox, which supposed to show that motion is impossible, is just the bisection theorem. But if you look at the other Achilles and tortoise paradox, that paradox is not the bisection theorem. That paradox is the division is done in the ratio 1:10. So how is that theorem, the division can be done in 1:10 ratio, supposed to follow from proposition 10 book 1? I don't know. So one of the people in this forum posted a question on the website, pointing me to a theorem, I think in book 6. I haven't analyzed that theorem in detail because I have not had the time to do so. But if anything, that might be where to look at for evidence of infinite divisibility, not book 10. Not book 1, proposition 10.
Okay, Hassa, did you have a question? Hassa, are you there?
Sorry, I stayed muted too long. No, I had only two short comments about this dividing line thing, because, like in the chat, we were discussing that the objection about infinite divisibility, it would be valid if you could say that every part, if you take all the parts of this line that are bisected together, they are the same as the original line. But after this bisection, these parts of the line have different identity. And I think that this might be related, this view, to Aristotle's metaphysical commitments, in which he thinks explicitly that the whole is different than the sum of parts.
Okay.
Metaphysically.
Okay.
So this is kind of metaphysical way of doing mathematics, which we don't do anymore, but people did.
Yeah, I agree. And I think you're right, because now we know, for example, that in the case of infinite sets, the whole is not necessarily greater than the part.
Yeah. That's another thing. Yes. Yeah. Good. Okay, but this is the only thing I had for now. So next question.
Wait, so upon asking questions through the chat, I'm seeing several questions, like from there's one from Lisa Shable. I'm seeing. Wait, so the original line is not the infinite divisible, but rather new lines are generated upon each bisection. Yes, I think this is what Proclus is claiming. At least that's how I'm reading it. And the new lines that are being generated are the ones to which proposition 10, book 1 applies at each stage. So it's true, actually. So okay, so I didn't go into detail regarding this issue in this presentation, but in my paper I go into more detail. So in particular, this geometric series with common ratio 1/2 is supposedly supposed to be a counterexample to this claim that you can have an infinite number of parts in a finite line. But I think this is why I'm saying that this issue turns on the distinction between points and parts. The reason why this geometric series converges really is that subsequent to a certain number of terms, the parts between terms is negligible. It's really zero, such that if you sum the already finite number of units of distance before a certain big N and add the parts which come after it, it adds nothing significant to the units of distance that you've already computed. And this is why this convergence works. And I think Berkeley's point, or what he wants us to take away, is that you can only have a finite number of units of distance in a finite line. And this is the argument we're getting from earlier on in the principles here. Okay, sorry. So does that answer your question, Lisa? Okay, thank you so much for the question as well. Let's see.
I see one more hand up from Alberto.
Alberto?
Mm-hmm.
Okay. Yeah. Okay, it's not typed in the chat box, so all right, go ahead. Thank you, Alberto.
Yes, it's a brief comment, a brief question about. I was, after seeing your slides, I was thinking if you consider, thinking specifically in Berkeley, if you consider his Conference of Infinites from 1707, which was a conference before the Dublin Philosophical Society, and it's interesting, or was interesting for me, because it shows Berkeley's modern influences. For example, in that conference, Berkeley criticized infinitesimals, specifically the John Wallis Arithmetica Infinitorum. And after analyze some specific examples of Wallis Arithmetica, Berkeley says or concludes that infinitesimals are merely nothing. And then he analyzed a controversy between a Dutch mathematician, Bernard Nieuwenhuis, and Leibniz. And it's interesting, well, at least for me, because Berkeley is underlining the problem of language, considering that specific topic of infinitesimals. And I just wonder if you, in some moment, you consider to analyze this, not only, of course, on infinite, as well as the the analysis and especially consider more Berkeley's modern influences, not only Aristotle, because of course it's in the root, but there are others.
Okay, all right. I think that's an excellent question. Thank you. I'm aware of this paper from 1707 that Berkeley appears in his collected works, but that's a talk that was given at the Philosophical Society in Dublin. Now, I think the issue of Berkeley's contemporaries who influenced his thinking, you mentioned in the Analyst and the other book from Wallis. I think you're absolutely right. These are certainly influences on Berkeley's thought. I have not looked into detail how Berkeley's views on infinite divisibility influenced his views on the calculus, but I believe there is a connection. Like one criticism he did have on the calculus, as you rightly pointed out, is that they seem to be contradictory, as at least as formulated in that century, namely the talk of infinitesimals or quantities diminishing beyond every quantity, and so on and so forth. So perhaps Berkeley's criticism of the calculus grew out of his initial thoughts on infinite divisibility. But that's something that I am perhaps going to pursue, or you might even pursue as a project eventually. But it's definitely something that I think is worth looking at.
Thank you.
Yeah.
I think there's a follow-up from Benjamin.
Yeah, thank you. Yeah, following up to Alberto's point about Berkeley's influences with respect to infinite divisibility and geometry. So far as I've been really kind of reading Berkeley, both contextually and really kind of textually, I was kind of always under the impression that Berkeley was really operating in his talk about infinite divisibility and geometry imagistically. And you had mentioned in your slides that he's coming at it from almost an explicitly metric or metrical point of view. And I wonder if you'd have more to say about that, or where you might be able to point us
okay.
in support of that. Yeah, that'd be great. Thank you.
I think this is the okay. All right. Okay. So I think you're absolutely right. So if you look at some of the arguments that Berkeley gives in the principles, one argument relies on what he says his inability to discriminate an innumerable number of parts in a finite line. So you might think that this is indeed relying on our intuition, or the fact that we need to be able to actually perceive distinct parts in a line in order for us to, and because we cannot perceive infinitely many parts, we therefore shouldn't believe that finite lines are infinitely divisible. And I agree that this reading of Berkeley has also been proposed by people who want to argue that Berkeley holds a kind of instrumentalist view regarding infinite divisibility, where he argues that whereas it is false, to strictly speaking, to say that the finite line is infinitely divisible, we can perhaps, for the sake of science, assume or take it as a useful tool for mathematics, because the finite line in itself is a sign of other even bigger lines than the one that you're considering. So there's definitely that reading. And as I said, I didn't develop that in this paper, but it's a subject of my other paper on Berkeley's mathematical atomism. Because I realized when I was working on this project that it was getting really big, and I had to pick and choose what I wanted to say within a reasonable amount of space. So I deferred this discussion, the one that you're bringing up, to another paper where we look more carefully at the instrumentalist reading and the relation between perception and Berkeley's argument regarding infinite divisibility, and whether in fact it is, what are the dependency relationships, for example? Does the argument depend on perception, or is it really Berkeley's mathematics or mathematical views that is driving the argument? So I will look at that later in the paper I'm working on. Thank you.
Okay, sure. Yeah, thank you. Just, yeah, I don't want to push you too hard on this, but it's so interesting, that you're coming from that perspective. I'm very interested in reading the fuller work on this that you've put out. But I've always read it the opposite way with the signification, that it's the numeral, the actual imagistic kind of length or whatever it is, the picturesque perception that we have is that which is signified by some such numeral or metric, not the other way around. Anyway, yeah, thank you. Yeah.
Wait, let me follow up on that. So you're saying that the numerals, like, so the numerals in what, in a line?
No, sorry, thinking about some such numerals, those signify some sort of like determinate idea we have of some such length or something like that. Yeah. Oh,
okay. I think I'm seeing what you're saying. So yeah, Berkeley has first of all, unlike Barrow, Berkeley does maintain a sharp distinction between geometry and arithmetic.
That's right.
So
yeah.
In particular, Berkeley thinks geometry is true. In the strongest sense possible, true, capital T.
Mm-hmm.
But in the case of arithmetic, he doesn't really believe that there's anything significant that's going on there besides just manipulation of symbols or numerals, as you're pointing out. And it's interesting to try to understand what Berkeley took to be the proper foundations. So if you've read the paper, I mentioned that the incommensurability thesis is arithmetical. And Berkeley, I think, is trying to dissociate this theorem, arithmetical theorem, from geometry. Mm-hmm. While incommensurability can be shown to be true, number theoretically, Berkeley wants us to notice that it doesn't imply anything about magnitudes or infinite divisibility of magnitudes.
Okay. Yeah.
Those are completely different results.
Great, thank you very much.
Yeah, thank you, Benjamin.
Scott?
Yeah, thanks again. So zooming out a little bit, I was interested by, I think just a couple times you threw in this sort of language of like there's real mathematics on the one hand, and then there's philosophy on the other hand. And sometimes it seems like Aristotle is on the wrong side of this, right? Because he's bringing philosophy and maybe metaphysics into something that is really just mathematics. Mm-hmm. And I thought that was an interesting sort of take on it. And I was actually curious if you think Berkeley sort of is in the same camp as Aristotle. Is he guilty of also conflating the mathematical with the philosophical, or do you think he's actually succeeded in avoiding this sort of pitfall?
I think that's a great question, and I think the answer is the following. I think Berkeley is not falling into the same conflation of mathematics and philosophy that Aristotle is falling into, because of the following reason. If you look at the postulates in Euclid, postulate 1, postulate 2, and postulate 3, you might be able to piece together some notion of continuity that is dissociated entirely from the philosophical thesis of infinite divisibility. So the only postulates you get from Euclid that can give you something like continuity are these three postulates. And again, this is very controversial. When I'm saying this, I'm not, because people have often pointed out that there are no continuity assumptions in Euclid's elements. But again, I think I thought about what these postulates 1, 2, and 3 are saying. And it seems to me that if you just take these as your starting points, you do not need to appeal to infinite divisibility as a philosophical position to develop the right account of continuity. Thank you. I think that's a great question. I believe, someone might, and again, this is why I think Gassendi's influence on Berkeley is important because Gassendi was one of the first people in the 17th century to insist that we need to distinguish the philosophical thesis regarding infinite divisibility of matter and the infinite divisibility of continuous quantities. So in particular, he wanted to be the case that physical atoms are real, something that Aristotle never would have accepted for philosophical reasons.
Great. Do we have any more burning questions? I had just one sort of semi-comical question to ask regarding Kenny's initial question.
Yes.
And so if I went to the baker and I ordered a baguette and I asked the baker to cut my baguette into thirds.
Yes.
And he takes out his knife and he makes one cut, cutting off 1/3 of the baguette, and then makes another cut. I could rightly say, you haven't done what I asked. You cut 1/3 off, and then you cut the second piece in half.
Yeah. Okay. All right. Yeah. But yeah, it's subtle. I agree. It's very subtle to figure out what the difference is. And I acknowledge that it's possible that we really don't have a distinction without a difference. But I've really struggled to figure out what could possibly be going on in this quotation from Proclus. And I've wrestled with several proposals. Maybe you have a better proposal of how to understand whatever is going on in Proclus right here. I don't claim that I figured it out entirely. But one proposal that I had is like, well, let's distinguish between the lines we're defining. And if we do that, then we are getting into this baguette example that you're giving, namely that you haven't done what I've told you to do.
Yeah. Well, if there are no other questions, we can all join together in thanking our speaker. And I think we should also thank, all the organizers, Western especially. You have a variety of possibilities to thank them. You can click on the clappy or thumbs up emoji thing, the text box, but I think I can speak for all of us that we had a really wonderful time. And I think this was a great success in sort of a very trying time. So thanks to everyone, especially the speakers. Benjamin, did you want to say anything in some?
Thanks everybody. I did have a few closing remarks, just briefly. Again, to echo what Aaron said, I'd like to thank everyone for all their work and their participation. I'm very pleased that we're able to offer you guys a venue to share your research and to discuss and get feedback for this. I want to remind people that I'll send the card for to Bro and Steve tonight after I get the update from Bro to see how he's done today. So if you want to be added to that list, so please email me, let me know. There is a survey that I'll distribute. I'll send it out to everybody on the registration list. So if you might get a couple emails about it. If you registered for all 3 days, please ignore the extras. I apologize for that. But I really would like to know your thoughts, your reactions to this, particularly whether or not this is something that you found to be fruitful, something you might be interested in participating in again or in future times. And then third, I just wanted to extend all of you guys an invitation. At Western, we have a research group that we focus on. We've been focusing on Berkeley. We've been reading some texts and getting together to discuss. We've been reading Stephen Story's A Collection of Essays. We're almost done with that. But if anyone's interested in a similar kind of format, we meet about once a week. It's been Tuesdays at noon, but I think we'll be moving to 1:30 Eastern time because of the Princeton Bucharest seminars taking over the Tuesday noon slot. So if you want to talk about an essay, you want to get more engagement, let me know and I'll add you to the list. And you guys are more than welcome to join us to continue that. Thanks everyone for participating in this. Thanks everyone for spending the weekend with us. And I wish everybody good luck. Thanks.
Thanks, Benjamin. Thanks, everyone.
Thanks, Benjamin. Take care.
Thank you, everyone. It was nice to be with you. See you.
Thank you.